Okay, the last topic that we cover in this class is HVAC efficiency. So what we're trying to do is get you familiar with some of the terminology that's used for these different pieces of HVAC equipment because unfortunately they've got a bunch of names for basically the same thing, and you need to be versed in that. First, let's review something from alternative energy, which was heat engines. So recall that heat engines are machines that convert thermal energy into mechanical energy. And I showed you guys a demonstration of one of those, the Stirling engine. There are various other types, but they all kind of have a similar diagram, so I'll just draw that for you. So we have two temperature extremes, a hot side and a cold side. We're transferring heat from the hot side to the cold side, but some of that heat gets redirected and transformed into mechanical work. That's the work output here. So if I want to know the efficiency of this heat engine, it's equal to the work output divided by the heat input. And I can write this diagram with energy as I've done here, or I can also write it with power. So I change this to a P, put a dot here, put a dot here, and that means thermal power in and out, and then mechanical power out. Recall that because of the laws of thermodynamics, there's a limit to how efficient any heat engine can be, and that's equal to the Carnot efficiency. So this is the maximum possible efficiency of a heat engine. It's equal to 1 minus temperature of the cold side divided by temperature of the hot side. And those need to be measured in Kelvin for this formula to work. Now, the thing to remember about heat engines is that sometimes the heat can come from different places. I mean, sometimes it's a combustion source, like the internal combustion engine in a gasoline car is a heat engine. But it doesn't have to be combustion. As you saw with the Stirling engine, Stirling engines are heat engines and they can run off any heat source. In that case, it ran off the heat in a coffee cup. So heat engines may or may not operate via combustion. Combustion is the most common type, but it's not the only type. So the thing about heat engines is they actually have nothing to do with HVAC, right? HVAC isn't responsible for creating mechanical energy. HVAC does something a bit different. It moves heat from one place to another. It moves heat out of a room that's too hot and dumps it outside, or it takes heat from the outside and puts it inside, or it takes heat from a fuel and puts it inside. So we do learn about heat engines though, because a very important machine in HVAC is the heat pump. And basically heat engines and heat pumps are the same thing but in reverse. So heat pump is kind of like a reverse heat engine. It's easier to understand heat pump if you understand heat engines. So that's why we cover heat engines. So I'm going to draw two diagrams for you for heat pumps. One is for heat pump in heating mode. So I still have a hot side and a cold side. I'm taking heat from the outside, which is cold, and putting it inside, which is warmer. And to do that, I am supplying mechanical work via a compressor. So heat pumps basically work using a refrigeration cycle, which you probably learned about in your HVAC class. So we supply mechanical work via a compressor, and we can transport heat from where it's colder to where it's warmer, which is inside. So let's indicate that's the room. Now I can run this heat pump in the reverse direction. And it's a little bit tricky here because I said that heat engines and heat pumps are the reverse of each other, but there's actually sort of two reverses. So if I reverse only the direction of heat flow, so let's say I've got the cold side here, which is still the room, and I am trying to make the room colder. So I'm extracting heat from the cold side and dumping it outside. And to do that, I still have to supply mechanical work. So you can see that I'm still extracting heat from something colder and putting it in something warmer. But physically, the direction has changed. Whereas before I was dumping heat into the room, now I'm taking heat out of the room, putting it outside. So this is for heating in the winter. This is for cooling in the summer. And we do that by using a reversing valve on the refrigeration part of the heat engine, or the heat pump, excuse me. Now the way we express efficiencies with heat pumps, and you got to be careful with that word efficiency. Sometimes people say efficiency with a heat pump, but what they really mean is efficacy. How effective is the heat pump at its job? Based on how much power I put in or how much energy I put in, how much heat can I move from place to place? And that's measured with something that we call COP, coefficient of performance. So the way we measure COP, the thing to keep in mind is that we do it from the point of view of the room. So if I'm in heating mode, my COP for heating is equal to the heat placed into the room divided by the work done by the compressor. If I'm in cooling mode, it's equal to the heat extracted from the room divided by the work done by the compressor. So in heating mode, my QH is the room. In cooling mode, my QC is the room. So in this case, I'm dividing the heat put into the room by the work, and here I'm dividing the heat taken out of the room by the work. Both of these quantities, QH and work, are measured in the same units. QC and work in the same units. Whether that's BTUs or joules doesn't matter. As long as they're the same, then COP is a dimensionless number, or unitless. And the reason I make a distinction between the COPs and regular efficiency is because these numbers can be larger than 1, larger than 100%. In a heat engine case, that's not possible because you always lose something in that transformation of energy. But here we're not transforming energy from one form to another. We're basically moving the energy. So we're moving heat from the room to the outside, or in this case, into the room from the outside. And here we're moving heat from the room to the outside. So because we're moving thermal energy and not transforming it, the limitations about our efficiency don't really apply. So these numbers can be above 100%, and they often are. I mean, if they weren't, then it wouldn't be a very good heat pump. So for example, if I have a heat pump and I can place heat equal to about 4 kilowatt hours for every kilowatt hour I supply to the compressor, then it would have a COP of 4. And usually for equipment there's a single number given for COP. Sometimes there's a single number, but it actually varies with temperature. So heat pumps have a certain temperature range that they like to function in, and if they get below that range, they don't work very well. So in cold climates, heat pumps don't work for the lower temperatures, so supplemental heat through some other means needs to be supplied. They also work, how they work performance-wise depends on other factors in the climate like humidity. So the important thing to remember, COP is dimensionless. There's another metric that we use called EER. EER stands for Energy Efficiency Ratio. ER is actually just like COP, except the units are different. In this case, I measure QH. I actually measure the power dumped into the room, so it's Q dot H divided by the power input to the compressor, which is P. This one is measured in BTUs per hour, like a thermal power unit, and P is measured in watts. And if I divide those, I get BTUs per hour per watt. That's my unit. So EER is measured in units of BTUs per hour per watt. Measures the same thing as COP, it's just that COP is unitless. I can convert between these because if I wanted to convert BTUs per hour to watts, I would simply multiply by 3.4. So if I I divide by 3.4. So if I have an EER, let's start with COP. If I have a COP of 4 and I want to convert it to an EER, I just multiply by 3.4. So EER is equal to 3.412 times COP. So if I have a COP of 4 here, I get an EER of about 13.65 BTU per hour per watt. Remember, my COP, no units, EER, BTUs per hour per watt. Okay, related to EER, we have a unit called SEER, SEER. This is the Seasonal Energy Efficiency Ratio. Now, the important thing to remember about SEER is that it's typically used only for cooling. And it refers to, over the course of an entire cooling season, how much energy is taken out of the space compared to how much energy was put into the compressor. So SEER is equal to how many BTUs we removed from the space in the cooling season divided by how many watt hours of energy we supplied to the compressor. So SEER has units of BTUs per watt hour. And you might look at that and say, well, in effect, that's exactly the same unit as we had for EER. Remember, for EER, we had BTUs per hour per watt. So here the hours is up here, but if I move it down here, I get this unit. These two units are actually numerically equivalent. It's just that by convention we write EER this way and SEER this way. And they're used for different things. So EER is used for, telling you how efficient the heat engine is at a particular operating condition. So at some certain temperature, you'll see this EER. Whereas this is, over the course of an entire season, it's kind of the average of weather for a particular area. So you have how many BTUs it uses, or how many BTUs it extracts from the room and dumps to the outside, divided by how much energy the compressor uses over an entire season. We can do the exact same thing with the heating side, except we call it something different. We call it HSPF, which is the heating season performance factor. HSPF is just like SEER, except it's for heating. Okay, so that's heat pumps. Basically, anything with a refrigeration cycle works like that. Then we come to furnaces. Furnaces can be electric, but they often burn a fuel. We call them combustion furnaces. So the furnace may burn natural gas or propane or something like that. So to talk about furnaces, we have a measure called AFUE, which is basically just an efficiency averaged over the course of the season. It stands for annual fuel utilization efficiency. So essentially, we burn some fuel over an entire season and total it up, and then we look at how much of that heat energy actually made it into the space. And the ratio of those two things is the furnace efficiency, or if we average it over the course of the season, it's the AFUE. Unlike COP, this number is always less than 100%. We're burning some chemical, most of that heat makes it into the space where it should go, and some of it does not. Some of it just goes up through the flue, either because of incomplete combustion or various other losses. So in practice, furnace efficiencies are somewhere in the range, typically 70% for older ones, to newer ones can be very high, 97%. Important thing to remember is that furnaces are not heat engines. Furnaces can be powered by combustion, and heat engines can be powered by combustion, but they are not the same thing. Furnaces are not heat engines. They are not limited by Carnot efficiency like heat engines are. So you can have a heat engine that's very high efficiency, that's typically much higher efficiency than a heat engine, but they do different things. A furnace is just responsible for producing heat, putting it into a space, putting it into an air stream, and then it goes into the space. Whereas heat engines convert thermal energy to mechanical energy, completely different. But I want you to understand those three machines: furnaces, heat engines, and heat pumps. They all do different things. They all have different numbers to describe them. So try not to get those confused. Now in the notes I provided for you a table that describes the heat of combustion for various fuels. And what we mean by that is, for say a gallon of fuel, how many BTUs do you get by burning it? That's what that means. So it's a way to calculate, how much, if you know how much heat you're going to need in a season based on the heating loads, you can figure out how much fuel you need if you know the heat of combustion and the efficiency. So that's a good problem to know how to do. One thing I should mention is that you'll see in the table that there's a range of values given for natural gas, and that's because in general the natural gas that gets piped into your home is not pure methane. Methane is natural gas, but natural gas also has various other impurities to it. It's also got an odorant added to it so that you can smell it, because methane is an odorless gas. So the heat of combustion of natural gas varies within some range depending on where the natural gas came from, because those impurities affect it. In this program, we typically use a value of 1,000 BTUs per cubic foot. So we say on average there's 1,000 BTUs in every cubic foot of natural gas. So a therm is equal to 100 cubic feet, which would make this a therm equal to 100,000 BTUs. So we use 100,000 BTUs for a therm, and this is how we convert between BTUs and cubic feet. So just be aware of that.